got here?
So this is a typical mollusk. This is a Trochus niloticus, and it's a typical seashell. You know, you find these sort of seashells around. And so this is what the Trochus looks like naturally. And so the animal's inside. It has a foot, and it walks very slowly along, along substrates. So this is what it looked like. There's a few layers of material here. When you polish it down, you get down to the mother of pearl layer, and this is what it looks like.
Wow. So that is this scraped
polished,
off,
right? And so this is the mother of pearl. It's a very strong layer, and you can feel. I mean, you feel it as a material. It's a composite material, so it's made out of 95% ceramic, calcium carbonate, and 5% polymer. So what we did was we took this sample, we put it in an oven at very high temperature, and that burns off all of the polymer. So you're only left with the ceramic, and the polymer actually holds all the ceramic together.
Ah.
And so this small amount of polymer makes it extremely strong. So if you look at it without the polymer, you can see, this is basically it, and it reverts sort of back to dust, brick dust,
crumbles like chalk,
like
right?
chalk, and you can see it here. I'd like to not break all of it, but you can see it here, and then if sometimes if you hit this, it'll break, but it's very, very strong compared to this, which breaks, immediately.
Huh. And so why would it be important for this animal to be so strong? I mean, there's sea slugs do just fine with nothing.
Depends on the predators, right? And so, in this case, there are a variety of different predators on these sorts on seashells in general. So, for red abalone, for example, otters come and try and hit them with rocks and get them. And there can be, for armored fish, there are birds that swoop down and get them, and they also fight among each other. So it depends on the predator. In this case, it has a fairly heavy and thick armor, because it moves fairly slow. The other thing that the predator of these guys, or of typical mollusks, are crabs that come up and they grab them and they sit there squeezing for days trying to break them. And so that's actually designed to resist this. This is called fatigue in material science, cyclic loading. There's a whole field of that in material science. And so if you look at the structure of these, they're actually designed to resist fatigue, cracking. So it actually has all these internal cracks that propagate very, very slowly during it. And so sometimes the crabs can give up and leave if they can't break it, or they can sit there for days squeezing and eventually break it.
Does the spiral design have anything to do with it?
It does, yeah. So, there's many different geometries of seashells. And so the geometry of the seashell also affects when something attacks it, its loading, what the stresses that it exhibits in it, as well as the underlying material. And so in most cases, armor is curved in nature. And we're actually studying why that is and how that is, all the different curvatures, and how that affects the stresses that it can withstand. And so there are ways that the stresses are redistributed through this geometry to resist attacks. And so that's obviously of interest for armor systems.
So can they do like a computer simulation of that and then just
we do that,
find out where the stresses are going?
Yes, we do that. We create entire computational simulations of the three-dimensional structure of the armor. Then we take the actual material properties that we measure of the armor, put that into the computational simulations, and simulate predatory attacks, bites, and all kinds of different things.
How did you get into this? You weren't a little girl going, I want to be an oceanic material scientist.
Well, I was trained as a material scientist in mechanics and also in theoretical and applied mechanics. And I had started out in graduate school developing composite materials. And it was kind of a natural transition. I was always fascinated by nature because it does it so much better than us. And we really look at it as a material. It is a material, it's a ceramic, it's a polymer.
Right.
And even though it's an animal, it's still a material. And so, we're just fascinated by the beauty and also the efficiency of these systems to create very, very strong materials out of things that are very, very weak. And so if we can do that, with synthetic systems, you can get orders of magnitude increases in strength, toughness, all these properties.
And have there been any famous discoveries by studying natural constructions that have already been applied to human inventions?
Yeah, there's many different what's called biomimetic systems. So biomimetic means that you're trying to mimic a natural system. But I would say that the field is really still in its infancy in terms of the benefits of actually being applied. And one of the difficulties is that it's very, very difficult to duplicate the kind of nanostructures and fine structures that are found in biology with the techniques that we have today.
Is there a goal to the research? Are you trying to, will you go up to some higher body and publish a paper, or?
We do publish papers on all of our research in the public domain, and the obvious goal is to be able to take all the design principles and apply them to create stronger, better materials. In particular, armor for structural applications, for human body armor, for vehicles, for buildings, etc. And so all of our work is funded, most of our work is funded by the Department of Defense in terms of looking at trying to understand design principles for those applications.
It may be hundreds of millions of years old. It may be the very definition of primitive, but hiding inside that lump of mollusk is a complex, really ingenious system that could inspire the high-tech human armor for the soldiers of the future.